go, push and record. All right, well, welcome again, Monday morning. We're finishing up 5.2. We're trying to solve our systems using what we call the substitution method, and we will then move on to 5.3 and another technique that we can use. So, see, most of you have gotten through that 5.2 homework. Good for you. But you know, might still be a few questions, and some of you are still waiting to get through it. So anyway, recalling our process here, sort of the recipe for using this this method, this technique. We have our two equations. We want to get one of them solved for one of the variables. Like both of these actually are solved for y, but then we can say that this expression is equivalent to y, and if we put it into the other equation instead of the y value in the other equation, we're actually combining the conditions that way, and we'll come up with a y value that works in both equations, or an x value to begin with. So we did a number of those. Once you've solved for the variable, you do that substitution, all right? Then you solve the resulting equation, and you're going to get either the x or the y alone. But then you always have to go back and plug that value into one of the originals to find the other variable. We're always looking for an ordered pair. I know I say that. We're always looking for the ordered pair, and then once in a while you'll see a word problem where they just want to know the x value. Well, you know, that's a word problem. Just read those carefully. Did they ask for both values or not? So this was one similar to how I finished up last time. We saw many of those where x's and y's were on one side. We had to pick one of the variables, choose which one we wanted to solve for. Well, these are both solved for y already. And so here's where like I said, I use that word easy carefully, but you don't have to do any extra work. This first step really is already done for us. And it doesn't matter, I could say, well, this is all supposed to be equal to y, so I could put it into the other equation instead of y. Just happens to be all by itself on the other side. Or I could have gone the other way. You're just going to end up with, you know, one expression on the left, the other one on the right. So here is that substitution step, right? Took that whole thing and said, if that's supposed to be equal to y, then here I am putting it in over here instead of y. And I end up with that then equation. This is now one of those types we practiced in chapter 2, where I've got a combination of x's on both sides and constants on both sides. So I want to get all the x's on one side and all the constants on the other side. And it doesn't really matter which side you go to. So let's say I'm going to add all the x's, basically canceling them out here and putting them over here on this side, right? Add those two x's. And now I'm going to add the 7 here to both sides. And, well, there I get down to 5x. It must be equal to 5. If I divide by 5, I get that x equals 1. And I hope you don't mind I turned that around like that, dividing both of those by 5. So there was the substitution, solving the equation, and I got my x value. I have to go back and figure out what the y value is. Choose one of the originals, or if you've actually rearranged one of the equations so that it's solved for that other variable already, you know, you could use that. But either one of these would be a good choice for us to plug this x value into. I just use the second one. 3 times 1 minus 7. And if you let me just finish that, that's what 3 minus 7 is -4. So there is the y value. Squeeze it in there. As an ordered pair, right? X first, then the y. There would be the ordered pair solution to that system. Work okay? All right, I know someone in particular asked me to finish up one like this. I'm not sure she might have come.
Yeah, I was the one. Can you just pause for just 1 second?
Yeah, I did change switch problems, so I made up one. I had one here that I knew the numbers would work out nicely rather than the one I made up on Thursday. So yeah, copy that all done. I was going to put up another one that made you deal with some fractions. We dealt with fractions here in a second, okay? Good enough, you ready? All right, no comment, huh? All right, here I go. I'm going to erase this one, all right? And number one, you notice somebody already mentioned, Thursday or Friday, did a forum post about this kind of problem, kind of explaining, talking you through number 5 and 5.2 is like this kind of problem. But here's something similar. I'm using examples from the texts since they usually work out nicely. So this one only has one fraction to deal with, but we'll have the same issue in dealing with it. But here again are two equations that are already solved for y. So that first step is really done for us. So I can choose to say, I'll just arbitrarily choose the top one here to put into this y. I could have gone the other way, doesn't matter. So the resulting equation, just like the last one, except the wrinkle here is I have a fraction I'm going to have to deal with when I'm combining those x values. So I think I'll leave these two x's here, and I'm going to subtract 3/5 x from both sides. Okay, so without doing that work yet, and just rewriting, there's what I have left. Looks a little thin, my new pen is kind of thin. So I'm going to need to combine those x's, but I'm going to add the 8 to both sides, which gets all the constants over on the other side. All right. So if you'll allow me, I'm just going to cancel that out, and this will be a 14 over here. Now let's see, I'm going to put all those, try to get all those x's together. All right. So this is like 2 over 1. I need to get a common denominator of 5 in order to combine all those fractions. So multiply by 5 over 5, that's the same as 10/5 x, right? Okay, just kind of doing that on the side. If you allow 10/5 minus 3/5 means I have 7/5 x. Got to talk that through without writing everything down, but I hope that works okay. All right. So there was the, little extra work, having to combine those two values. And I think the one that number 5 in 5.2 that you have to do that similarly has two different fractions. So you just find that common denominator for both of them and then add them together or do a subtraction like this one. Well, now I need to get to 1x. How do I cancel that? That's where you multiply by its reciprocal, right? If I multiply both sides by the reciprocal, 5/7, now I'm going to think of that as 14 over 1. All right, that gets those to cancel, leaving me just x. Here, that's nice. I got a little bit of canceling I can do. Divide that by 7, divide that by 7. And that looks like 2 times 5. X is a 10. Let me know if you didn't follow something there. All right, so I solved and I found my x value of 10. I have to go back and find the y value. I can plug it into either one. It wouldn't be too bad because of this 5 in that one, but might as well use the one without fractions, right? I'm going to squeeze it in right here again. Y equals 2 times the x value 10 minus 8, and just adding that up this way. What's that, 20 minus 8? A 12. Y is a 12. a couple larger numbers than many of the answers we run into. Not at all unusual. So I did just want to finish up as requested. A couple problems in that shape. You can set one right side to the other right side. You know, they're both equal to x's, so just make them equal to each other. If that's good enough, I'm going to move on then, okay? Here I go. I'm going to read.
Real quick, sorry, I'm literally getting through the problem and I'm trying my best to catch up. I literally just got to the part where I was able to get to x equals 10 on my own. So I never actually got to watch how you, same thing with the last problem. I feel like I'm running behind what you're doing. I don't know if it's that you're going so fast that I can't keep up or I'm going too slow, but I'm literally missing the last part of the equation on how you get y both times. And this is the second time. So is there any way you can go over that part with me or with the class one more time? How I understand how you got to x. I was able to keep up, but
Okay.
now I don't know how to get to y.
Well, for both this technique and the one that we're going to do next, you found one of the variables. Then you always have to go back to one of the original shaped equations and put that one in, right? So here I put this 10 into the first equation. I wrote it here. I put it in for the x, 2 times the 10. And there's the rest.
Okay, so whatever equation you put as the beginning equation is where you're going to plug in your original x value that you got.
Well,
so just like on the last one we did, you would have plugged it in to the negative 2x minus 2 problem.
you know,
That's what we plugged in first on the left-hand side.
if I could get
Is that right?
I'm sorry. If I could get you to step back and sort of think big picture, it doesn't matter which one. Okay, it could have been the first one. It could have been the second one.
Is it just whatever equation you plug in on the left-hand side is going to be the one that you're going to plug the x into?
So I chose which one looked like it was easiest to work with. I chose the one without the fraction. So I could have put the x in here and I would have gotten the same value eventually. If I
Okay, so it really doesn't matter. You can just pick any of the two problems, plug in that x, and either way you're going to get the y value.
Right, and if I recall, maybe I have equations that look like this, right? If I had one as part of a different system, if I had one that looked like this as one of the two equations, I'm just making up something. I'm not going to solve this right now. But maybe I would.
Well, really quick, before we get too mixed up adding in something new, I see where you did the y equals 2 times 10 minus 8 equals 12 to get the y for 12. Can you plug it in for the y equals 3 over 5x plus 6 and show me if you get 12 too? Just can we go over that together before we get too off track, adding in a whole nother set of equations to try to go over?
Well, can you do that? Plug it in.
Yeah.
Well, plug it in. There, I plugged it in. What do you get?
So 6 over 1 plus 6. So, okay, 12. Okay, so y equals 12. Okay, so that's great. So either way. All right, thank you.
I also wanted to point out, here we're, you know, I do try to present this material as the concepts that you get to use to change things around rather than always exactly this way. That's like trying to follow a formula, and you need to try to be flexible enough to look at the problem and see what it is that you have to work with and what you need to do. Students often run into difficulty when they say, how do I do this kind of problem? I memorize what to do. How do I do this kind of problem? I memorize what to do. There's too many different things. What we're trying to get you to do is understand the processes and what's legal. It's always, you can add the same thing to both sides, or you can multiply or divide both sides by the same thing. We're doing those same processes. This here was one I was just trying to make up to emphasize it doesn't have to be even one of the original two. These might have been the original two equations. Maybe I would choose to solve this one for y by subtracting the x's. But this is just another version of that same equation. If I had solved this system and came up with the x value and needed to find the y, I could plug it into either one of the first ones, plug in the x and find the y, or this is just the same equation been rearranged. I could use this one and it's all ready to tell me what the y value is. So try not to get hung up on which one to use as long as it's a version of one of the original equations. You can use whichever one looks like it's easiest to work with to find that other variable. Okay, so changing to 5.3. So far we've used graphing, which works if you're really careful about drawing your lines, and that happens to nicely meet at the intersection of the graph grid, but that's sort of the limitation. Then we had our substitution method. 5.3 is called solving using the elimination method. Oops, squeeze it in over here, okay? All right. Now, some of your problems, when you see them on homework or the test, will ask you to use a specific technique. Solve this one by graphing, and you have to graph it and show the solution. Solve by substitution, and you have to use that technique. Or solve by elimination, and you'll need to use this technique. Some will then just say solve, and you get to pick which technique looks like the easiest to solve that particular problem. Just want to make that clear. If it says to use a certain technique, you're going to need to use that technique. So just start with basic concept here. Here's an equation, right? It says that what I have on this side is equal to what I have on that side. We've over and over been adding and subtracting the same thing to both sides. If I add C to both sides, it's still true, right? As long as I'm adding two things that are equal to each other to both sides, I still have an equation that should be true, all right? Well, even if it looks more complicated, as long as the two things are the same, supposed to be equal, we can add them together. Now, here's a system, all right? Supposedly this expression equals 10, all right? Those two things are equal to each other. Here's another one. Supposedly these two things equal 20. They're equal to each other. So this equals that. It's like C equals C. I can add, now I'm just going to add this side of this equation to the first one, and I'm going to add this side of this equation to the first one. It's like here was the A and the B, and these are both C because they're equal to each other. So I can add this side together, and I can add that side together. Just kind of like an arithmetic problem. Draw the line and add them. Look what happens. Here, I add up the x's, and I get 5x. Here I add up the y's, but they cancel each other out and go away. I have eliminated the y. Now this one was specifically set up ready to go, so that was going to happen. We're going to have to do a little work on more of them. But that's the basic process, is get one of the coefficients, the numbers here, to be same size number and opposite signs. So when I add them together, they cancel out. Then I'm left with an equation with only one variable. Dividing by the 5, I get that x is going to be a 6. Don't worry, we're going to do a bunch of these. Of course, and just like the last examples, I need to find the y. I can go up here and choose either one. I'm going to choose the first one. to find the y value, right? 12, subtract the 12, and y must be a -2. That's just like the substitution method. Second step or last step, find the other variable. My ordered pair, 6, -2. The process, though, was all up here. What I did by adding the two equations together, when the numbers were just right, I got the y to go away. Okay, do it again. I'm going to do it again, all right? Here goes. All right, very similar. This again will be a situation where you might have to make a choice. Which variable am I going to try to eliminate based on the numbers that you have there to work with? Again, here's one that's like ready to work, right? Ready to go. If I was to add those sides together, got to make sure I add those sides together. The y's are all ready to cancel each other out. So the work will be to get the same size number on either the x's or the y's. We'll practice that more in a minute. And once we get to that point, now we're ready to add the two equations together, and that will eliminate one of the variables. Add all the x's. If they're not in the same order, you got to put them in the same order, right? If they try to trick you by make it y plus x, you know, make sure you're adding x's and x's and y's and y's. And what's that, 9? Divide by 3, and x is a 3. Got to plug it back in to find the y. Maybe I'll use this one this time. 3 minus y equals 4. If I subtract the 3, negative y is 1. I guess y then -1. If I multiply both sides by -1, I'm not guessing, right? My ordered pair is 3, -1. Sorry, let me get my examples handy. Where'd it go? There's that other page. All right, another one. All right, 4x minus 3y equals 1, and 5x minus 9y equals -4. There's the system. If I just tried to do this technique right now, add them together, you know, 9x's minus 12y's, I've still got x's and y's. Nothing's going to be eliminated just by adding what I have right now. So I need to decide, I need to do some work to get the numbers to be the same size. Same absolute value, same size numbers, but opposite signs. Okay. So I could look and say, well, it's basically the least common multiple. What's the smallest number I can turn both of these two into? You know, a 20, I can make 20s out of 4s and 5s. Oh, but look at, I could turn this one into a 9 pretty easily, right? I could, if I multiply that entire equation by the right number, this will become a 9, right? I'm going to take this entire equation. Here's my, eventually I sort of cheat and just use one big parentheses. I want it to be opposite sign also. That way when I add, they'll cancel out. I could leave it the same sign and subtract, but we make more mistakes when there's subtracting and lots of negatives. I'm going to choose to make this a positive 9 by multiplying both sides by -3. I'm multiplying the whole equation, both sides, by -3, so it's still true. And here's where I do my
I don't know if I'm the only one, but I am so lost. This is not making any sense.
Well,
Is
just
there
watch
any
for a
way
while,
to be
okay?
more clear as to why we're doing this? Or I don't know why I'm so lost. This just doesn't make any sense.
Okay, well, try to watch for a while and see if it starts to make sense, okay? We're using a different technique that eliminates one of the variables. Adding the two equations together, if it causes one of the variables to cancel itself out, then we have a simpler equation with only one variable in it. So this is another method we can use to do that, get down to one variable. When we did the substitution method, it was so that we could get rid of one of the variables, and the whole equation was a combination of only one kind of variable, all x's or all y's. This is another way we're doing that, getting it to be all x's or all y's. The way that it happens is if the numbers on the x's or on the y's are the same number with opposite signs, then when I add them, it will go away. So it would be easy to get, here I'm looking at those four numbers I have to work with. Do I want to, nothing's obviously the same. So I have to make them the same in order to use this technique. I can, when I look at the choices, I would have to multiply this whole equation by 5, I could get 20s. And this whole equation by 4, and I could get 20s on the x's. But it's simpler, less work if I just multiply to make a 9, make 9s for the y's. So I'm going to multiply. What number will turn this into 9? A 3. And I want it to be the opposite sign, so I'm going to use -3. Here I go, -3 times every term. -12x for that one. Here's going to be plus 9y, and here's going to be -3. So there, I just made all the numbers proportionally bigger, but this is the same equation as the first one.
That doesn't make sense. Why would you need to times I don't understand it either. I don't understand what you're doing there. Why you
Okay, thank God someone else is saying something, because I am so lost.
the adding the ones that were you
Yeah, the original ones we were
the original one I understood, but this one I don't understand.
Yeah, I was totally with you until you started this equation.
Same.
Can I say something?
Yes.
It would be helpful to do the little arrow thing that he does and just kind of bring it down below and work on the problem so that it's not so messy. In my opinion, this totally makes sense, but I'm just trying to get it to like not be so messy on the board maybe, and it might make a little bit more sense, I'm not sure.
You can't cancel out the 3y minus 9y. He has to make that 9y a positive 9 on the top. So it cancels each other.
So the y's have to cancel each other?
Yes.
Oh.
If I add them together right now, if I thought this might be helpful and add them together right now, I still have one equation that has two variables. I can't solve that.
Okay. I get it now. Okay. So you have to, one variable has to be canceled.
Yes, that's what
Okay.
the elimination is.
Okay. 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 Thank you.
How am I going to get them to cancel if they are the same size number with opposite signs? How do I get them to be the same size number? I'm going to choose one of the equations. At this point, I could choose only this first equation, and if I multiply it completely by -3, it's going to turn that into a positive 9. So here I'm going to multiply this entire equation by -3. All right, rewriting it down here. That becomes positive 9. And that becomes negative 3. Now here's the first equation. I'm sorry, there's the second original equation. There, I changed this one just by multiplying it to get that number specifically. Now if I add them together, the 9s happen to cancel. Negative 4, I miscopied it, right? Negative 4. I'm going, oh shoot, fraction. Divide by that negative 7, I get x is a 1.
Kayla, does that make sense?
It will eventually. I'm gonna just hope that on the next one I can keep up. Can you do another one just like this so I can start fresh from the start with you guys on another one?
Yes, I need to finish this one.
Oh yeah, when you're done. Yeah, when you're done.
So now I need to find the y value. I can plug it into the first one. I can plug this x value in the first one. I can plug in the second one. And if I thought there was a reason to, I could plug it into this one I changed. But I don't want to do that. That's got bigger numbers anyway. So I'm going to plug this x into, I'm just going to choose this first one up here. So here I go, 4 times 1 minus 3y equals 1. So that's 4. If I subtract the 4, I get negative 3y is negative 3. Divide by negative 3, I get y is a 1. Well, that just happens to be 1, 1. Okay, yes, another one, just like it. Here we go. Pardon me. I'll let the whistle here. Now, like the last example, none of those variables will immediately cancel out just by adding them right now. So I need to look for you might say, what's the easiest variable to get the numbers to be the same size? The x's or the y's? In order to get the same number on the y's this time, I'd have to multiply both equations to turn both into 10s maybe. Sometimes we're going to have to do that, both equations. But this one, here I could get the x's to both be 6s without too much messy stuff, right? How about I multiply the first equation to make this a negative 6? So I'm going to try to make this into a negative 6. What do I have to multiply by? A negative 2. The whole equation, both sides, I'm going to multiply by negative 2. In my presentation, if it works nicely, I usually just, okay, I'm going to rewrite that below the existing one here, okay? Multiply every term by negative 2. Makes this negative 6x. Makes this one negative 4y. Makes this one negative 4. There, I forced that to become the number I wanted it to be. Now, if I add them together, those x's are going to go away this time. And I found the y value. This one, it worked out better to eliminate the x's. As always, I have to find the other value. So I'm going to plug this 4 in for y. I think I'll use that first equation again, just because it's smaller y values, smaller numbers. 3x plus 2 times the 4 that I found is 2. subtract that 8. Now I can divide by 3 and get x is -2. Careful now when you write your ordered pair, right? We found the y first. This is the x. Make sure you put your x value first is all I'm getting at. All right, one more time, I'm going to try to find one just like that and leave you to do it. Have you get started on it, okay?
So in the last one we did, they had to cancel out perfectly. Like we changed the -3 into a +9, so the y's would cancel out straight across the board. And I see that's not how this one worked out. So how are we to determine what number to multiply that first equation by? Is it just whatever the y value is? Because
Okay,
that's
so
what's it's confusing me, because in the first one,
I understand your question. Now answer it, please.
Yeah.
I looked at the numbers here I had to work with, right? I have to choose either the x's or the y's. It doesn't have to be the y's. It's whichever one looks like it's easier to get the same numbers on. Here I would have had to change them both to come up with a common number. I can't just turn 2 into 5 without multiplying by decimals or fractions. But here, it looked like it would be easy to turn the x's into 6's. So I chose this time to eliminate the x's instead of the y's. So by this being a 6, I could change this 3 into a 6 pretty easily, as long as I multiply the entire equation by that factor of -2. So that's how I chose what to multiply by. I wanted to become -6.
okay, I thought there was a rule with this that the y's had to cancel each other out. So that's not the case.
Correct. I never said that.
Okay, I thought that was said by somebody that the y's are supposed to cancel each other. Okay.
One variable needs to be cancelable. Whatever variable is easier to change, you change.
Okay, I'll have to work on this with my math tutor.
You pick the one that looks like it's the easiest to cancel out. Whoops. That's not the part, not the one I want. Oh, sorry. Make sure I get two equations from the same system here, not mixing examples here. Oh, right, watch my signs or it'll be totally messy, totally wrong. Okay. Like the last time, they're not going to cancel immediately. So I get to pick which variable, which is going to be easier to get the same numbers on, the x's or the y's. The closest number I could get for both of those would be 21, and I'd have to change them both. But the x's here I could change for this one and make them the same. Can you try that one, if that makes sense? Here's where I would probably just have to rewrite the first equation, and then I'll change the second equation. I want to make sure you're on the right track. I'm thinking I'm going to multiply this entire equation by -5 to get the x's to be the same but opposite signs. Because it's the second one I'm changing, I'm not just going to, try to write it down here again. I'm going to copy them both down again. Here's the first one. And now I would, rewrite the second one. Distribute, multiply -5 times each term. change signs, right? Why does it scare me here? Negative 22. It's going to be, oh, 44. Yeah, all right. Is that okay for you so far? I got that one to be negative 5. Of course, it changes every term, right? Every term is being made that proportionally bigger. Right? Adding them this time again, the x's would go away. Negatives, lots of negatives. Negative 22. But that's positive 44. Divide by the negative 22. Did that make sense? Now I have to find the x values, right? Need to find the x values. So if I plug this y value in, pick one of them. Looks like maybe this is smaller number, so I'll plug it in the second one here, okay? X plus 3 times negative 2 was the y value we found. That's to equal negative 3. That negative 5 was part of the next step, huh? X minus 6 is negative 3. If I add the 6 to both sides, squeeze it in, sorry, x is 3. And the y was negative 2. Did that work for you? Let me know if it didn't. Okay, well, on to the next. Sort of alluded to this, but sometimes you're going to have to multiply both equations. All right. Very first examples, the numbers are ready to cancel out just by adding them. These last 2 or 3 examples, I was able to multiply one of the equations and get the numbers to be the same size. Looking at the numbers I have to work with here, you know, I can't just multiply the 3 and turn it into a 7 easily, or I can't do that with a 5 to turn it into an 8. I'm going to have to come up with a common multiple, kind of like a common denominator idea. Not a fraction, but just saying, what's the smallest multiple I could turn those both into? 3 and 7, I could make them both 21s. 8 and 5, it would have to be 40. Would I rather go to 21 or to 40? I think I'm gonna do the 21. So there's the choice. You know, you see, what could I turn those both into? Oh, one number. What could I turn those both into? All right, which one's smaller or easier to work with or something like that? So you're making a choice. So this time I've got to multiply both equations to get to that common multiple. So I'm going to make this first. Yes?
So would one of,
Pardon?
so when we multiply both of the problems, do we have to multiply one of the problems by a negative?
In this case, it depends on what signs they have to begin with. Here I'm going to get to 21s, and one will be negative. I will have to use a negative. I will choose to multiply one of them by a negative so they are opposite signs.
Okay, so just the one. Okay, thank you.
I don't want to overemphasize that it has to be add, but so if you just, before I finish that, just imagine if I had negative 3x and a minus a 3x plus a bunch of y's. You know, what if the x's were this? I could I could subtract, right? -3 minus a -3. It's just too many minus signs. So that's where I was just saying we make more mistakes when we're subtracting, especially when we start mixing in lots of negative signs. So I always work to get them to be opposite signs by my multiplying. Then I can add and they cancel because they were opposite signs. So I'm going to make 21s out of both of these. Let's see, I mean, I'm going to choose to multiply the entire first equation by 3. So that'll be positive. So to get to 21, I need 7, but I want opposite signs, so I'm going to choose -7. I'm going to get a big number over there. Oh well, hopefully it works out nicely. Okay. So first equation, everything times 3. 21x plus 24y equals 12. Second equation, everything times -7. -21x. Minus is going to be plus 35y. I don't know what that is. I'm going to do 7 times 27. Pull out your calculator if you need to. 14, 189, and it was positive negative, so -189, big number there. Just happened. Now I'm ready to do the adding because I've got these to be the same. So this is the more complicated ones where you have to multiply both equations. So what did I get here? 59 y's is, I'm going to subtract the 12 and it'll be a -178.
177.
177, but good, because I was thinking, wait, that doesn't work. Excuse me. And so now you got to divide by 59. Maybe you'd like to use your calculator, but that is,
-3.
yeah, worked out nicely. All right. Again, I think if the problem started with fractions, you might get some fraction answers, but in general, otherwise, I think most of your homework problems are going to end up with integer values, whole numbers or integers. I found a y, I still have to find the x. So, well, I'm not going to use the bigger numbers. I'm going to pick one of these original equations before I multiplied it. I think I'll put it into this one right here, okay? And see if I can squeeze in here and you're okay with that. 3x minus 5 times -3 equals that original 27. I'm going to go over that way. That's plus 15, right? 3x plus 15 equals 27. Subtract the 15. 3x equals 12. X is a 4. Okay. There we go. 4, -3, xy. We're out of time, but we'll come back and we'll do more of these tomorrow. We have, I think, pretty good, we have time in our schedule.
Thank you. Thank you. When you did it a couple times over, my brain started to understand what you were doing. So just thank you.
That's why, well, it takes time. You just kind of got to watch. I know you're trying to copy them down, see if it starts to make sense where it's going and what this process is doing. Right. And eventually some people they say, oh, I like this better than the substitution, or vice versa. Like many things, if you've got two different ways to do something, some people like one better than the other. Okay, well, finish up 5-2, right? And get that in tonight, and we'll carry on with this tomorrow. All right, have a good day.
Bye.